Hello. Hey guys, welcome. And this is part 4 of the paper solving in latex, right? Fixed paper solving in latex. So, in last video we did up to 20, and let's move on to numerical answer type. And start with problem number 21, which is quite simple. I think kinetic energy of the particle is increased by 2%, then we have to find out with what percentage momentum the particle will increase. So let's turn on the integer answer type. Yes, so now we have the answer in the square bracket, and then we can proceed from question number 1. So let's get it just started. So yeah, as you can see, Copilot suggesting apply the equation of kinetic energy, and let's see. And I think let's accept this answer and try to run it, and then we can modify this answer. So it's starting from 1 second. We have to start from new line, right? Cage yes, page, no, line break, yes, line break, and oh yes, no, this is weird. Let's leave it as it is. We have to do a lot of things to get this right. So firstly focus on the solution part. So apply the kinetic energy equation, so yeah, it's right, and apply the equation of momentum, yeah, it's right. Apply the equation for percentage change, but this is where it got wrong, because in the percentages the power should be multiplied. So no, this is wrong, but we can complete this part pretty easily. So let's start with kinetic energy. Kinetic energy is equals to p square upon 2m. That means p square or we should start with fundamental, I don't know. And I don't know what should I do. I think we can let's just start with a relation between kinetic energy. Apply the equation of kinetic energy versus momentum, or say linear momentum will be much better. Yes, linear momentum, and then we can proceed directly from here. Kinetic energy is equals to p square by 2 m, right? And then we can differentiate both sides with respect to time, yes, right? And delta k delta p square by 2 m, yes, seems right. And as the continuous 2%, let's run it first. Let's run it first. So as you can see, we applied the equation of kinetic energy versus linear momentum, p square by 2, and then we can differentiate. So yeah, 2 will get cancelled out, dp upon dt, and from there we can apply some magic here into text. No. We should firstly like delta k, yes. Delta p, and then we can divide both of it. By kinetic energy, and then k p square by 2m. No. We should yes, this is right, and then it will solve automatically. That will be much better solution. Say goodbye. M will get cancelled, P will get cancelled. So it is doing, I think, wrong simply. We should say 2 times delta P upon P. And now multiply. 60%. So yes, 21 is done. It's quite long, but I think we can proceed along the sorter method. I think we can just multiply with the power, but in this way I think this is better. So yeah, let's move on to problem number 22. So this is each and every step. Then he or she can create their own sorter form. It doesn't matter is it long or short, but a first person should understand the solution. Most of the time we make the solution for a student. So yeah, students should stand every step, and then here should make it shorter in their own way. That will be much better. So apply the equation of conservation of energy, apply the equation of conservation of momentum. Yeah, that will be so I think yes, solution is right here, but the description is not right. Yes, we can conserve the momentum, but why the velocity for the both will be common at its maximum height? I don't understand this. Yes, we should describe here. यहाँ पे भी हम लोग डिस्क्राइब करना पड़ेगा कि क्यों एनर्जी कंजर्वेशन हो रहा है. Let's fix this. As you can see, there is there is no friction, which means only conservative force acting on the system. Hence we can apply the conservation of mechanical energy, right? So yes, this is the correct version. But before that, it's solved perfectly, but I don't know why it's wrong. Because as you can see, in the equation of mechanical energy, it just put it half mv square, which is totally wrong, because we have to assume the system, mass of the system, which is m plus capital M. So copilot is good, but not in the analytical thinking. It's just completely like auto completion tool. So let's fix this. But first of all, we should focus on the momentum part. That will be much better thing. So let's move this part up, and we have to describe here firstly. Once okay, let's continue. We got an interrupted in the middle. So here we firstly have to describe why these both will move with a common velocity at its maximum height. So as we can see, as you know, the page is smooth, there is no friction. No man, this is not we have to describe the situation here. I think particularly the situation. The situation is like this. As you can see, situation. This at the path, as the wedge is smooth, which means no. There is no external force acting on the system, along x-axis, along horizontal direction. Hence we can apply the conservation of momentum. And at the moment of maximum height, both these masses will have the same velocities will have the same velocity, because there because the surface is because path for the smaller block is curved and as soon as is curved, and if there is a relative velocity between the masses, there will be and if there is relative velocity between these two masses along x, along horizontal, then there will be there must be a there must be a vertical component of velocity for the smaller, which is not possible for maximum height. I think there is no external force acting on the system along the horizontal direction. Hence, we can apply conservation of linear momentum. At the moment of maximum, both these masses will have the same velocity, because path for the smaller block is curved, and if there is a relative velocity between these two masses along the horizontal, then there must be a vertical component of velocity for the block for the small block, which is not possible for maximum height. So yeah, now we can conserve the momentum, and as you can see there is no friction, which means only conservative for static conditions. We can apply the conservation of mechanical energy. Yes, it's right, but we have to fix here that m plus m. Yes, now it's right, and then this was the equation. So should v in the equation of conservation of energy, and this is how we can get the desired result. Yes, so now it's correct. So yeah, let's move on to problem number 23. Making solution for the other people getting quite tough. Like you can solve like by thinking the idea in your own hand, but whenever you have to explain someone it gets quite complex. Pretty complex. So let's complete this copilot thing, and then we can change pretty much anything. 1 second, apply the equation of continuous linear momentum. Yes, yeah, it's correct, because system A isolated net force in x will be 0 because tension at the collision. Once again, yes, tension is an external force, but at the moment of collision, tension will be in the vertical direction. That's why we can conserve the momentum in the horizontal direction. So yeah, it's perfectly right, but we need to describe here. And energy, we can yes conserve the energy for the system. But why we need to conserve energy? Can we do with some other measurement thing? K is equals to 2 is wrong actually. It's wrong because it's saying that the system has to complete the vertical cycle. That means system have to have the mass, have to have the velocity 5 gl. So yeah, it's solving the wrong way. So let's delete all this crap, and from where we can start. No energy conservation, nothing like that. We just have to apply conservation of conservation of linear momentum. So elastic, let's as the collision elastic hence the ball, m hence the velocity, as the particle is moving with velocity v naught, as the collision is inelastic, as the collision is inelastic, inelastic there is some linear momentum. No, this is not the correct explanation. And the collision is once again elastic, and particle sticks with the ball, hence we can apply the conservation no, apply and the collision is inelastic and particle sticks with the ball after collision, the system will have a common velocity. So equation from the boundary. As no force, no external force, external. So this is right. As the collision is inelastic and particle sticks with the ball after collision, Con velocity. Apply the equation just to notional forces acting on the system. Another notion. V, and then we can say no. If energy is not enough in a vertical circle and has to complete the velocity at the lowest point should be equals to lowest point should be equals to under root the square root of 5gl which means right arrow mv naught. V naught and k is equals to 5. So yeah, yes, it's correct. As you can see, now it's totally correct. We just applied the momentum conservation along x, and we can remove this line. Actually, it doesn't matter, but yeah, for the reader it's fine. And then one more thing I'm feeling uncomfortable with is using under 5 gel, which is kind of lame because not everyone will remember this information that we require under 5 gl, which is common by the way, but I think this would apply the conservation of energy, but for right now it's fine. I think, yeah, for right now it's fine. So we should leave it that way, but we can do it in a much longer way, but that will negate the point of studying circular motion. So let's leave it that way, and let's move on to problem number 24. Let's see, already it has been 28 minutes and we only solved like 3 questions. So let's move on to problem number 24. 24 is kind of important question, or you can say quite tricky, because at the first glance you will have no clue what should I do to solve this problem, but after some applying some common sense you will get the idea, and it will seem quite common. So let me explain the problem. So a solid sphere of mass m of radius r is initially rest on a rough surface, right? And by q, maybe an arrow or something hits the sphere at each height from the center of mass, right? And then after hitting, a sphere starts to roll without slipping, which means it is in pure rolling motion, and we have to find what is the value of h for which this to happen, like for which a sphere to roll perfectly on the surface. So we have no idea q about the q, but we can assume if it is a q, a small q or arrow or something, it has some linear momentum. It must be has some linear momentum. That means q will change its linear momentum. That means q will impart some linear impulse on this sphere, and that linear impulse will get converted into angular impulse for the sphere. yes, q is moving along the straight line linear. Q is only doing its translation. That means q can only provide the sphere linear impulse, but the sphere will get in terms of angular impulse, and from there we can apply some angular impulse equation, and we can solve it out. So what should I do? We can apply torque. No, torque nahi. Angular impulse. Angular impulse. R cross J is the angular impulse, but that will be like quite lame to use directly. Let me calculate on the paper first. I think there is no paper. Where is the paper? 1 second. So yeah, let's say angular impulse. How much impulse will get translated into angular form here? Let's describe first. As the sphere is hit by q at that edge of the center, the sphere will have linear velocity and angular velocity. A sphere will have a linear velocity and angular. Yes, it's right, but I don't want that. I want is like from the center, I omega. Yeah, it's stalling. Can we do some interesting thing? I don't know. Q will apply an impulse on the surface is called the change in linear momentum. Apply an angular impulse. Apply an angular impulse on the surface cause to the sphere. Yes, as the sphere is free to rotate over the center, to the angular will cause the angular which cause an angular angular impulse cause change in angular momentum. Yes, this is right. So no, r cross j, I think vector r times vector j. J is linear impulse and delta L. Yes, this is correct. So Q will apply an angular impulse to the sphere and delta L. That means, say simply, r minus h. The particular distance is h. So h dot is equal to delta L. No, we can apply delta L is equals to omega I omega, right? I omega and h j is equals to I omega is equals to v by r, right? Diffrac. V by r, and you can put actually 2 by 5 m square diffrac 2 by 5 m r square c dot no h j is equals to 2f5 mbr, yes, right? Or 2 by 5 2 by 5 j r बोल सकते, and then h so yeah, as you can see, we applied the equation for the angular impulse, and we can say that the sphere will also get a linear impulse due to the velocity in the x direction, and that will cause a change in linear momentum of the sphere, which is exactly equal to the impulse imparted over it. So yeah, that's right, and j will get cancelled out, and h will q will apply an angular impulse to the sphere, which will cause change in angular momentum, and as the q is hitting the sphere, the distance, yeah, this is right. I think one more thing I have to do is we should describe about the j, but this is not common thing, but I think let's leave it from everything should not be described. And let's move on to problem number 25. I think 24 is over, although I'm not satisfied with the solution completely, because we have to do, I think, few more things in that, but let's see. 25 for I know. I think we have to draw some diagram here that will do the job. I think we can center, we can take picture, and we can separate this out. I think yes, right, but I don't feel comfortable. Like, let's get this thing copied over here, and we can maneuver that. So let's run it first. Actually, we have to define a few more things. Let's delete every node. Node is not important for the description. Platform is okay, teaser line is okay, Omega is also not okay. We don't need anything because in the picture everything is described. TZ velocity is okay. Let's run it first. And yeah, this big thing is not important or important. I don't know, not important. Let's continue this one. So yeah, it's perfect, and now we can save this thing. So platform is south at top log, right? So we can separate this thing. Let's delete this part at 3 times r. Let's run it first, then see what we can do. Oh yes, both are separated now, and now we can add some line. So this will have the velocity like center. We should calculate something. I think we should add node, that will be much better. Let's add node instead of circle. So node is easy to kind of maneuver things. So let's circle, and then let's say this is ring, and at O, let's say 2. So no, oh, one thing, we are getting wrong this new line. So let's run it first. Yes, so no, there is no pulley, large pulley. Let's let's say L pulley. I don't remember, but I made some node thing. No, I think we have to check something. Where this is. So we have to go cd text and then cd v test paper. No, v test paper. And unless we can read this file, and then we can see what is the node for the yes S pulley, S block, L pulley, which is large pulley. But we can draw thick, everything we can change. So for right now, just use L pulley. L stand for large. So L, then save it. It will run accordingly. I think not enough large. So where is this? Yes, we can just copy this whole part. Or we should describe a ring. I don't know. For right now, just leave it that way. I can do describe everything on later part. So yeah, as you can see, minimum size should be, let's say 15 mm. No distance doesn't matter actually for right now. So let's run it first. 15 is not enough, that means we have to use 20. 20 is still not enough. Let's say 25. No, 25 is not enough. 30. Yes, so it's fine. Now we can I think draw vector quite easily. So first thing, we have to draw a TZ line, and this time we can just refer ring dot north and this time we have to move because omega is towards anti-clockwise, that means minus 1.5 comma 0, and left part, and there we can use v naught, let's say v naught minus r omega, p naught plus r omega. So yeah, as you can see, this is right. This point will move towards the right, and we can once again apply a TZ line, and this would be over to minus 2 comma 0, which is v naught, and towards left, and let's run it first, because we are assuming velocity of center of mass is v naught, and then accordingly we are just doing velocity for the points. And one more thing, dot south, but this time we have to say minus, right? So now we can apply the equation. This is over, I think. Then we can proceed with the equation. So yeah, as you can see, we drawn some vector thing. Firstly, every contact point should be indicated with some velocity, right? So topmost point will move with v naught plus r omega, because center of mass is moving towards left, and that means r omega will just add up the velocity, and at the lowest point v naught is towards right, sorry left, and r omega will right. That means we have to subtract this two part, and velocity at A and B will be v naught plus r omega respectively. Yes, that's right. Let's run it first, then we can solve some later. So yeah, it's quite easy, I think. Momentum conservation is not no, momentum conservation should not be applied. We can say no. Momentum conservation, although I can do, but here we have to do like for pure rolling, contact point must be relative velocity must be 0. At contact point. So at contact point A, velocity is equal to v. No, I think and v naught is equal to r omega. One more thing I have to describe into text because there is no information about v naught. So we just assumed assumed assume that uh, assume that disk है या cylinder है disk the disk is rolling the disk is moving with velocity, the central mass, and with velocity v naught towards left. So first thing, where is wrong? Yes, r omega equation 1. So we need to discuss to r omega, and then we can put the value for r omega. We need to discuss to r omega. Yes, it's right. And then from here we can replace into text. Yes, substitute. Suggestion but right. Velocity at point. Yes, right. That's right. So yeah, so we would not in equation of k is equals to 2. R omega is equal to r. Yes, just that. So yeah, 25 is done. Let's move on to 26. I think we are online for an hour about. So let's continue. Let's finish this paper. I think 5 problems are remaining only. So let's move on to problem number 6. In problem 6, there is a spring attached with a rod, and rod is pivoted at one end, which is fixed, and there is no friction. I think I guess, but we have to assume there is no friction because friction bridge will like apply some torque that will negate the point of energy conservation. So long uniform rod of length L, mass m, is free to rotate in a horizontal plane over the vertical axis through its one end. A spring of force constant K is connected between one end of the rod and the ground. When the rod is in equilibrium, it is parallel to the ground. If the period of oscillation is T, then find the value of axis. So we just have to apply the equation of torque. We do not have to draw like drawing ridiculous stuff. So we are gonna do fast, and just we have to draw some. Hello, sorry, I got interrupted in the middle. So let's move on to 26. So we were talking about the torque equation. So let's apply the torque equation. Talk about the point of hinge. It's right. and the torque is minus kx sin theta. I think yes, it's right. We are not gonna explain everything, as already included. The torque should be 0. Oh, this is messing thing up. Torque is I alpha, so I alpha, and sin theta should be theta. One second, not x sin theta, L sin theta, L sin theta. That means L theta. Enter text for a small acceleration, for small acceleration, sin theta plus theta, right? Let's run first. Where is the problem? Alpha, theta, everything's fine. Where is the problem, man? I don't know. Let's delete. No. Torque alpha. Let's read the log file. Missing line number 913. Where is the 913? Yes. Where is the problem? Let's delete this line. This is the problem of latex. Just doesn't provide any concrete error message. Why it's getting wrong? Still it's wrong, and I don't know actually. Inter text. Oh man. Yeah. Apply the equation to this is fine, and then we can say I alpha is equals to, yes, this is right, and then we can alpha is equals to, yes, again this is right, and now we can put alpha is equals to I का वैल्यू पुट करना पड़ेगा यहाँ पे, which is ml square by 3. That means it will get, yes, this is right, and alpha, that means omega square. So yeah, it's right. Just we solve the torque equation, we find the omega square, then 2 pi by we can apply for the temperature 2 pi by omega, then on comparing equation we got the value of x. So I think we have to do few commenting on here because we just applied directly, so we have to add into text. Yes, compare with the equation of, yes, this is right, and then apply the equation third time for this. This is fine. Yeah, it's okay. So x equals to 3. Let's move on to problem 7. We have to do first because we are like spending hours and hours over these solutions. So 1 second. Yes, so we can start from here. No. Solution. Again, I'm not gonna draw anything. Just we can apply the conservation of conservation of angular momentum. As you can see, two discs have their own. Let's say, I don't know what it is doing. Let's make it a smaller little bit. That is how we can see. Let's complete this. No, complete until this line, and then add. Sorry, then once again. So let me solve. Apply the equation of conservation of angular momentum. Yeah, it's right. Either discs are rotating about the same axis, angular velocity of the system will be perfectly right, no problem. And now apply the equation of kinetic energy, half I omega square. Yes, so system has the moment difference I1 plus I2. Yes, omega is right. We solved this equation quite well. Yes, and then we can solve half I diffraction I1 I2. I1 I2. Yes, let's learn it first, then we can see what can I do. If we take the common I1 I2, then we should not be having I1 I2 in the equation. So let's run, and again this will get removed. That means bracket also we have to remove, and let's run it again. Oh yes, so we got it right. We just took the common I1 I2 and separated it, and now we can I think yes, this is right. So half I1 I2 upon I1 plus I2, which is right, omega 1 minus omega 2. Somewhere something is wrong. I don't know where it's wrong. Loss in, oh sorry, loss in kinetic energy we have to find of the system in the process. So actually we found out the final kinetic energy, that means K we have to subtract it from the initial kinetic energy. Oh man, we have to do it again, the whole thing. The loss in kinetic energy. Oh. Loss in kinetic energy is given by, yes, let's run it first. See, so it will take a half. Yes, no, it's totally fine, and then we can proceed. Yes, let's run it first. Half I omega, yes, totally fine. Yeah, this is what I wanted. Yes, perfectly fine. And let's run it first. Half I omega square, yes, we complete the whole square thing, and after that let this coparallel thing complete. Yes, we took the LCM, I guess, or not. No, we just took the common out of it as half, and we changed nothing. I think we changed nothing. Yes, nothing. And maybe in next line we can do some crazy thing. So yes, I1 I2. Oh, it got wild. I1, no, it got wild. If we took the LCM, that means no, it's not right, because we will have the extra term here. I1 square omega 1 square omega 1 square and plus then this term, and again we will have omega 2 square, sorry, I2 square omega 2 square square, and then we can proceed that. Yes, so yes, we got the right thing. No man, still I am not satisfied with it. Or am I? Let's see. Yes, until now it's correct. Let's complete this thing. Yes, one I two. Yes, everything fine. Yeah, everything is fine now. We can take common out, and yes, it's fine. It's fine. It's fine. And then we can separate this out. Yes. So as you can see, everything is fine now. We can separate I1 I2 as a separate unit. Then we can compare this with the given equation, and we will have the value of k, which is 2. So yeah, perfectly fine. Let's move on to rule number 28. So I don't think you need an explanation for this solution. We just apply the conservation of angular momentum because net torque is 0 for the system, and then we just calculate the loss in kinetic energy, which is ridiculously long. So have to be careful in this calculation part. So let's move on to 28. And in 28, I think 28, oh man, मेरा मन नहीं कर रहा सोल्व करने का. A particle mass 250 gram is equal to SM under a specific force mass 25x. The particle attains a maximum speed during the, it's quite simple. Apply the equation of SM and differentiate 1 no, it's quite long actually. Maximum speed. So let's apply the equation of SM. Kx. We should a sin omega t. Let's complete. No. Ma is equals to minus kx. A is equals to minus k by n. So here we can see that. No. I'm lost. Oh man, I don't know. Yes, we can see k by m and omega square maximum speed. Yes, let's continue with (0.4), which is not right actually. Maximum velocity is omega. मुझे सोल्व करने का मन नहीं कर रहा. And actually mass is in gram, so we can put 240 upon 1000. As that in maximum velocity 4 upon a. Yes, it is. We can apply directly equation for the maximum velocity equation and the particular distance of O, that was for is equals to A omega. Yes. Mass, and we put it mass as 250 grams. That was K. I don't know what should I do. Sometimes co-pilot thing is weird. You just lost your mind doing trivial thing, and you don't know where to fix because you're just fixing things, and it takes more time fixing things. Let's omega. I don't know. Into text. K is equals to 25 and M is equals to 0.25, yes, 250. Amplitude 250 upon 1000 in the equation of the equation. I think this will solve the problem, yes. So yeah, as you can see, first we don't need to do all these part equation. Directly we can use K by M, and on comparing equation we got this part M is equal to 2 because we have to convert into kg because force is in Newton, and we got this part A is equal to 40 centimeter because amplitude is in one more thing. We messed thing up, man, because velocity is in meter per second. So how can you say 250 10 will get cancelled 100? So this should be 40 meter. Oh, I lost my mind. Let me do it manually first. Actually I did it, but I don't know what I did. So force is equals to minus 24 Newton, minus 25x, yes. That means if we compare force equals to minus kx, that means we have k is equals to 25 in SI unit, and mass is 250 upon 1000, which is the mass also in SI unit. And now we can apply velocity is equals to A omega, and velocity is 4 meter per second. A omega, we have to find A omega is equals to under K by M. So A is equals to under K by M upon 4. So just we have to delete all this. No, this. Compare with the equation f is equals to minus kx. Yes, so k is equals to 25, and mass is equals to 0.25. No, yes, 0.25. Yes, right. And then velocity is equals to 4. Now apply the equation of the equation for maximum velocity. Which is v just omega. Yes, right. Then right, no, yeah, this solution is quite perfect. So yes, we found, apply the equation of maximum velocity is omega. Now we found out, I think we should find omega here is equals to v by 10. Yes, I think it's okay, but we did quite long. So let's leave it 28. I think that's enough for now. Let's move on to solution 29. So 29, there is a system of two spring has the different spring constant k1 k2, and in between a small block m is attached, and if the frequency of the oscillation is f currently, and we have to find what if we just change their spring constant. So if both k1 k2 are made 4 times the original value, the frequency of oscillation becomes k times f. Then find the value of k. Exactly is the same. Yes, let's complete then. See what happens. Actually answer is wrong. Answer actually 2. So whatever, apply the equation of tempered. No, let's keep it that way. Parallel k1 k2. Yes, okay, substitute k in the equation. Yes, so apply the equation. So for right now this is fine, and from here as the frequency inversely proportional to the square root of the spring constant, if the constant is made 4 times, this frequency will become half. No, twice. So from here let's delete k1 and k1 dash कर देता हूँ, k1 dash and k2 dash. K1 dash is equals to 4 times k1. Yes, this is fine. And k2 dash is equals to 4 times k2. Then f is equals to f dash. F dash is equals to half 5 to 5. Yes, let's proceed with that. F dash, yes, let's proceed with that. Yes, let's proceed with that. Let's see what we got here until now. So oh man, 4k, it's not right. Half should be actually 2 should be no, from line number It's wrong here. Not K. 4 times K1 K2 88. And then K1 plus K2. Yes, it's right, and 2 will get a bird. 2 C dot. Let's sum it up. So yeah, 2 got a bird, and this will get 12. Yes, so yeah, the value of K will be 2 because let's not describe it. Let's move on to 30. I think you will get the idea what we did. So solution is not difficult, but the formatting solution in latex is quite tedious. Right arrow, then begin, and this is the last problem, and we have to finish this. So a ball of mass 1 kg is attached to an inextensible string. The ball is released from the position as on the figure, and the impulse imparted by the string to the ball immediately after the string becomes taut is under 2k. Then find the value of k. So as you know, it's a question of linear impulse, because the ball suddenly got change in momentum and a string will get taut and it will feel a jerk, or that jerk be like assume as the linear impulse. So we just have to find the change in linear momentum, right? No problem. So not the conservation of linear impulse. Into text apply the equation for linear impulse. Linear impulse as change in linear momentum. Yes. So linear momentum is, so linear J is equals to change. Yes, it's right. Oh, you just did it. Let's say capital J is equals to, if we drop this body 1 meter, that means actually it will drop 2 meter, because this is the taut point and it will get like here. So from here to here it moved actually 2 meter. So its momentum will be I think let's leave it here and add 7 x. Ball will move 2 meter distance. 2 meter distance before a string becomes taut. Hence the velocity will be 2g. Yes, it's right. Hence, yes. Hence, that means so yeah, this is the final. So as you can see, we applied the equation for the linear impulse, and we find out the velocity at the moment when the string becomes taut. which is square root of 2 into square root of 10, and then we apply the equation of momentum, which is jmv2 k will become 10. So yeah, this is the final solution of the problem number 30. Oof, I got it. Some relief here. So thank you for joining me on the stream, and I hope you have learned something. Otherwise there is no point in joining, right? Spending hours and hours on a live stream. I think we are live from live since 1.5 hours. So thank you, and see you in the next live stream probably. And by the way, you can hide this solution by just deleting this part. As soon as run this document, you will get only the document, program. So as you can see, this is only the paper, and still solution is in the document text part, but it's not getting rendered. So as soon as we replace the argument as #1, you will see the solution get rendered in the PDF. So yeah, and you can do hard thing for the option as well, but I'm not going to do here. I think my work is finished here. So thank you. See you in the next.